So let's start. My talk is about what's new in VoronoiFVM.jl. So that's a kind of talk which kind of is based on the idea that I already gave a talk in 2020 on VoronoiFVM, and then I just I'm supposed to tell you what's new, but before I tell you what's in it anyway. Okay, so that's a package to solve coupled nonlinear systems of partial differential equation of reaction diffusion convection type. Ah, there are no slides? Wait a minute. Ah, that's me. So wait a minute, what's that? File output, enable presentation mode. So what's going on? So basically I have presentation mode on. That's normally what is going. Ah, no, it's okay. Yeah, okay. Okay. So that's, yeah. So VoronoiFVM.jl is my package. I have something new since 2020, and I tell you what's in there. It's a solver for coupled systems of PDEs on domains in 1D, 2D, 3D, which also can be just any geometry. And basically, I'm working with reaction diffusion convection equations, which have some storage terms under the time derivative, some reaction terms between the species in the system, and some fluxes, which also can be coupled, and some sources. So they can also depend on the solution. It's all nonlinear, but they can also depend on position and time as well. And also basically a notation for boundary conditions where I described them just also as nonlinear functions. It's some kind of coupled nonlinear Robber boundary conditions, if you want to put this way. And I'm using the 2-point-Plux finite volume method. So the idea is that I take my domain omega, I triangulate it using just creating a Delaunay triangulation. Then I can create the Voronoi cells, which then serve as control volumes, and then I can use the Gauss theorem in order to cast the integral over the divergence of the flux over the control volume into some surface integral over the fluxes with the neighboring control volume. And for the Laplace operator, for instance, I'm getting out this kind of finite difference equation, which then is a discrete approximation and discretization of the continuous system. So this can also work in 1D or in 3D. And for the whole system, I get a coupled nonlinear system of equations. So this is basically for the discrete implicit Euler time step. I have these nonlinear flux functions now, which basically replace the continuous flux by some finite difference flux expression, which can all be coupled or nonlinear. I have the reaction rate terms and so on, and the geometry factors kind of coupling these things. And this is a nonlinear system where the number of unknowns is the number of species in the system times the number of nodes in the grid. And yeah, so that's a method which has nice physical properties like maximum principles, positivity of the solutions. If these are present in the continuous problem, also we can show some nice discrete thermodynamics like entropy production estimates and so on. And also some divergent disadvantages, in particular if you want to solve hyperbolic systems. It formally would work, but not very well. So in that case, you should use Trixie, which is focused on that kind of partial differential equation systems. So how does this look like in the API? So basically I can create a grid. I describe a flux function, as I said, a source function, and I describe the bounding condition. So I cramp this in here in the Pluto notebook cell, and then create a system, and then I can solve. And I can easily change the grid and solve this in 2D. And yeah, so you can see it. So I can get the solution in 2D, and also just so with the same physics, I can solve this also in 3D. And I can get just the visualization of this stuff in 3D, so with the same boundary conditions. Or I can change, okay, so that's a Pluto notebook, of course. I can change just one of the parameters, making this really nonlinear, and I get the solution of the nonlinear problem out of this. I can also make an error removing the const, which means I will get allocations in my hot assembly loop. So user is warned to kind of be careful with this. Okay, so what's behind? So storage of unknowns is just a dense or sparse matrix. I use Newton's method to solve nonlinear discrete systems. I avoid global sparsity detection by calculating local Jacobians and putting them together into the global sparse matrix by an extendable sparse package which I wrote. And and then, okay, solve linear systems. I'm using LinearSolve now, and we can also use ordinary Differentiability.jl in order to solve time-dependent problems. And also I have a multiphysics feature in there, which means I can have different species in different subdomains. Here, for instance, I can have 3 species, one coming in here, reacting with a second one, which is transported, and then reacting to the third one, which goes out there. And so I can solve this also, yeah. And I can, here I'm using the default solver. I just can switch to some solver from the ordinary diffix. So I can create from my system, I can create an ODE problem and use all kinds of ODE solvers for these PDEs. And this amazingly works also for 2D, 3D, and it's faster than my kind of default solver. I'm amazed by this ODE system package, and I can switch methods and so on. This all works quite well. Yeah? Okay, and I also have a couple of accompanying packages which I maintain together with my colleagues, like preprocessing, meshing. I have a package called Simplex Grid Factory, which makes a simple way of describing discretizations, triangulations, for instance, in 2D. Oops, that's a syntax error here. And oops, and should be, of course, like this. Okay, yeah. And I also maintain the triangulate.jl and detection.jl packages for meshing. Grid management I'm doing together with Christian Merdon mainly, who has also a sibling finite element package on the same kind of package ecosystem. And for post-processing, you have seen now a code which I call gridvisualize.jl in connection with the PlutoVista.jl, which basically enables 3D visualization in Pluto notebooks based on VTK.js, so making it in the moment faster than Makie. I hope at some point I can also use Makie for this. So it already works, so there's a Makie backend, but it's, so not completely perfect now in the Pluto notebooks at the moment. Okay, so what's new? Basically, I worked on since 2020. I really learned step by step things from the SciML ecosystem, and I tried to make my package compatible to this, like using LinearSolve, common solve interface, ordinary diffig.jl, you have seen this. The interface, I'm also using the recursive array tools.jl, so okay, sorry for the wrong markdown syntax here. I can have now discontinuous quantities with jump conditions at interfaces. I just working on preconditioning, like equation block precondition for these coupled systems. Some various model additions like outflow boundary conditions, edge reactions, different coordinate system, velocity field projections. Currently I'm working on multi-threaded assembly, and also I have ideas how to couple now with modeling toolkit, which could describe or create me my kind of callback functions for describing the system. Maybe even symbolic index interface.jl could work, I don't know. But modeling toolkit really works. A student of mine really made great efforts to couple some Python code to Julia with this kind of intermediate representation for modeling toolkit, so it can work, and I want to have this. Okay, and we are using this for semiconductor device simulation, solar cell modeling, electrochemical reactions, chemical reactors, performance. So Roman Scherer is also at the JuliaCon. He uses this for modeling of flow battery cells, and I have collaborators on reactive mixtures in porous media, geothermal two-phase flows. And I'm also teaching advanced topics from scientific computing at TU Berlin, and a couple of the ideas behind this you can also find out in the course, which is online. So thank you very much.